We're now going to have a look at the actual classes of antibacterial drugs. So we're just going to go through these drug targets and have a look at what drug classes we currently use to kill or control bacteria in these areas. Try to sort out the classes in your head and tag them to the areas of attack, those classes. So starting with the cell wall, which is unique to the bacteria, and certainly our cells don't have it, so it's a very obvious point of attack. So let's have a look first at the drugs which target the cell wall synthesis. So basically there are two major areas of drug classes that do this. The first major division, which contains a lot of very widely used antibacterial drugs, are the beta-lactams, because all of these drugs have in their chemical structure what is known as a beta-lactam ring, and it actually isn't a ring, it's more of a square. And so all of the drugs that fall into that category have that ring in their structure. And the other type are the glycopeptides. So let's just have a look at these two. So the beta-lactams will contain drug classes that you will recognize, I'm sure. Under the beta-lactams we include the penicillins, one of the first antibacterials to be discovered and used. The cephalosporins, which came later, the carbapenems and the monobactams. The penicillins and the cephalosporins have been the most widely used, and these carbapenems and the monobactams have been developed later on and probably come into use as the penicillins and cephalosporins drop out of use. These drugs are bactericidal, and they have two problems. These beta-lactams suffer from resistance problems. The bacteria have developed resistance to these types of drugs largely by producing an enzyme known as beta-lactamase, which degrades any of these drugs belonging to these groups because it attacks the beta-lactam ring and breaks up the molecule that way. So there's large problems with bacterial resistance to these drugs, and there are also problems with allergic reactions to a number of these drugs. So if a person does have an allergic reaction the first time that they're exposed to a drug, then they really shouldn't be given that drug again, because there is a risk that they will have made antibodies against that drug, and there's a risk of anaphylaxis the next time that the drug is used. So those are two major problems associated with the beta-lactams. And the other broad grouping of drugs that attack bacterial cell walls are the glycopeptides, and these are much less widely used, or have been. They are now starting to be used as the last line of defense against resistant bacteria, and these include vancomycin and teicoplanin. The problems are these are much more toxic drugs, they're much more likely to give adverse effects, and they tend to be fairly narrow spectrum. Now the spectrum of an antibacterial defines how many different bacteria it's able to kill or stop growing. So a very broad spectrum drug would be able to control both gram-positive and gram-negative bacteria, a whole range of species of bacteria. Narrow spectrum may be just gram-positive, just gram-negative, or just certain ones within either of those categories. So the glycopeptides are only used really when the person can't take the beta-lactams because they've shown an allergic reaction to them, or when there are microbes which have developed resistance to the beta-lactams, and therefore the glycopeptides now are your only chance sometimes to address some of those infections. Okay, so let's just have a look at some of those beta-lactams. We've got the top two on the list here, the penicillins and the cephalosporins. These are the two that we're going to look at. Anything that belongs to the penicillin class of drugs you will recognize because it will have that -cillin ending. So penicillin G, there's also penicillin V, procaine penicillin, ampicillin, flucloxacillin, amoxicillin. All the cillins are penicillins. Then there's the cephalosporins, and they help you by having either a CEPH or a CEF, a KEF, at the start of the names. So cefalexin, cefamandol, ceftriaxone, cefapime, and so on and so on. So if you see the KEF, it's a cephalosporin. If you see the cillin, it's a penicillin. Both beta-lactam groups of drugs, because they have that lactam ring, or actually that lactam square in their structures. That means, therefore, if a bacterium develops resistance to these drugs by making beta-lactamase, then you will get resistance to both penicillins and cephalosporins across the board. That bacteria will be resistant to all of those drugs. Penicillin, let's just have a quick look at this. You probably have heard this story before. It's one of those much told stories about a serendipitous finding. How penicillin was discovered to have antibacterial properties, essentially. Alexander Fleming, the scientist that you can see here, was working on culturing bacteria in his little dishes, as you do, in his lab, and he'd left some windows open and some mold landed and contaminated his bacterial cultures. And when he came to have a look at his bacterial cultures, he found the ones that had been contaminated by mold, that there was a clear zone around where the mold was, where no bacteria had grown. There was no bacterial culture in the area of the mold. This is penicillin mold here. And that's how the antibacterial substances produced by mold were discovered. And that's what has been harnessed in the form of antibiotics. Because these are living things, they're just like all other living things, they have to try and stay alive in spite of being attacked by all sorts of other things, and so they produce their own protective substances in the same way that we do. Everyone has to defend themselves if you want to stay alive. So molds produce a range of antibacterial, antimicrobial substances that are designed to protect themselves, and those are what we have harnessed in the form of antibiotics, and the first one was penicillin. So of the penicillins, those that have a letter designation, in other words penicillin V or penicillin G, are actually the natural forms of penicillin from the molds here. They can be used, but they have a very short half-life and they have a relatively narrow spectrum of activity as well. But you do see them used sometimes. But most of the penicillins that are around now are actually synthetic, so they're not produced from the mold. They're synthesized in the laboratory according to the structure of the substance produced by the mold. So examples would be amoxicillin, ampicillin. These synthetic versions that were produced later also are better in that they have a broader spectrum of activity, so they're active against gram-positive and gram-negative bacteria. And flucloxacillin and dicloxacillin, which were later still, also have a degree of beta-lactamase resistance. So these ones can still be effective against bacteria that produce beta-lactamase. So that's quite useful for penicillins to have some that are beta-lactamase resistant. Fleming and some associates that worked on how to produce penicillin on an industrial scale so that it could be used won the Nobel Prize. And even fairly early on, when he accepted the Nobel Prize, Fleming was warning about the problems that would likely to arise with the use of antibiotics, or penicillin in particular. And here was his warning. The time may come when penicillin can be bought by anyone in the shops. Then there is the danger that the ignorant man may easily underdose himself, and by exposing his microbes to non-lethal quantities of the drug, make them resistant. So he was foreshadowing what has come to pass, which is the development of resistance by widespread use of antibiotics like penicillin, and particularly underdosing or inappropriate dosing, failing to finish the course of an antibiotic. All of these things contribute to the development of resistant bacteria. This is not for you to learn, but this is just for you to see that there's a whole range of beta-lactams, and many of them I haven't actually mentioned, but there's the penicillins, there's the cephalosporins here, but there's other ones. Here's the carbapenems, which came later, and the monobactams. There's various groups of beta-lactam, and here you can see the beta-lactam ring in each of these structures, which is what they all have in common. So the resistance of bacteria to beta-lactams is because bacteria have acquired a resistance gene which allows them to produce beta-lactamase, which attacks that lactam ring and breaks down the drugs. So as I said, the newer generation penicillins, flucloxacillin and dicloxacillin, are beta-lactamase resistant, so they don't get broken down. Their lactam ring is protected from beta-lactamase. And so these ones can be used against resistant strains of bacteria. MRSA here stands for methicillin-resistant Staphylococcus aureus. Staph aureus is a bacteria that is commonly found on the skin, but in surgical wounds or other types of wounds, particularly in a hospital environment, those bacteria can invade and cause really nasty infections. There are now many strains of drug-resistant Staphylococcus aureus, and MRSA, methicillin-resistant Staphylococcus aureus, essentially means that there is only one drug left that these bacteria may be sensitive to. Flucloxacillin and dicloxacillin may still be active against MRSA, which is good. After that, you have to go to vancomycin, which, as we've already seen, it has the same. It also attacks the bacterial cell wall, but it's a much more toxic drug. So it's good that there are some penicillins that still have this resistance to beta-lactamase. However, the ones that don't, that aren't resistant to beta-lactamase, is the broad-spectrum ones, so they're the ones that are really useful and nobbling all kinds of bacteria. You can combine them with clavulanic acid, which, as you might have noticed in this family tree here, is a beta-lactam itself, but it doesn't have particularly powerful antibacterial activity. It has some, but it actually inhibits beta-lactamase, which is very, very handy. So very often, if you're using the broad-spectrum penicillins which have no protection against beta-lactamase, they will be combined with clavulanic acid, which will give them protection against beta-lactamase by inhibiting the enzyme. So there's a couple of different ways to evade this beta-lactamase and therefore reintroduce activity of the penicillins. One by using flucloxacillin and dicloxacillin, or by combining clavulanic acid with the penicillins that are not resistant to beta-lactamase. So we're fighting back a little bit on that front. What else with the penicillins? Well, the penicillins have a tendency in certain people to produce an allergic response, and it is in about 10% of the people who are given penicillin. And the allergic response is the kind of things you would expect with an allergic response to any drug, really. Often a rash, itchiness, swelling on the skin, around the face, around the lips, or as you can see on the back here, anywhere on the skin really. Anaphylaxis, which is your systemic hypersensitivity response, which can be life-threatening and which would occur on the second exposure to a drug that you're allergic to, occurs in many fewer people. So 0.01% roundabout would be the rate at which penicillin would actually cause full-blown anaphylaxis. But 10% or so of people do have allergy to penicillin, which would mean that they really shouldn't use it again. Nor should they use any of the other beta-lactams, because the likelihood is that there will be cross-sensitivity to those as well. So that if somebody takes penicillin for the first time and has some kind of allergic type response, then you would have to assume, and it may not be so, but to be safe you'd have to, that they would also be allergic to cephalosporins and any of the other beta-lactams. Often those people will carry a bracelet, so that if they should be in any situation where they're not able to communicate the information themselves to members of the medical profession or healthcare professionals, that the bracelet can do it for them. Because you really do not want to be given penicillin if you've had an allergic reaction to it previously, or a cephalosporin. So this is just, again, not to learn, but this is traffic lights which are giving you advice about what you should do if somebody shows an allergic response to a penicillin. On the red light there, and you would not use any penicillins. Amoxicillin and clavulanic acid combination, which is known as augmentin, flucloxacillin, any of the penicillins would definitely be out. You'd have to be very careful using the cephalosporins, because there'd be cross-sensitivity in not everybody, but a proportion of people. You would probably base it on how severe the allergic response to penicillin was as to whether you'd risk a cephalosporin or not. If it was a relatively mild response to penicillin and there's a reasonable bet that cephalosporins will be okay, then you would probably risk it. If it was quite a severe response to penicillin, then you wouldn't risk giving a cephalosporin. But what you could use would be any of the non-beta-lactam antibiotics, that is, antibiotics that belong to other groups that we haven't talked about yet. You notice that vancomycin, which is one of the other group of drugs that we talked about in relation to cell wall destruction, is there, but it's at the bottom of the list, because you certainly wouldn't go to that straight away, as is ticaplanin. So that's allergies, which can be a problem. So cephalosporins, these are also beta-lactams. They're also derived from mold, antimicrobial, that is produced naturally, in other words an antibiotic. It's produced by a different mold, Cephalosporium, hence the name the cephalosporins. They're useful in that they have a much broader spectrum of activity than the penicillins. The natural penicillins, of course, had quite a narrow spectrum of activity. There are now 4 generations of cephalosporins. The first ones had a narrower spectrum of activity, and as we've gone through the generations, the spectrum of activity has increased, but also the resistance to beta-lactamase. So in the later generations of cephalosporins, we've got drugs that are more useful because they have a broader spectrum of activity, but also more likely to be able to kill bacteria that produce beta-lactamase because they're not affected by the beta-lactamase. So these numbers here are just indicating the generations. You don't need to remember that as usual. I'm not going to ask you to rattle off names of cephalosporins or any other kind of drug, but you can see it's easy to recognize them. They start with the Ceph. It's a cephalosporin. Okay. So if these drugs act by nobbling the cell wall, I hope you might think that it would stand to reason that they might be more effective on the gram-positive bacteria, which is true because the gram-positive bacteria, remember, have a thicker cell wall on the outside. But the broad-spectrum beta-lactams are able to attack both gram-positive and gram-negative bacteria.